Oh, I think it wants to pick it up. Yeah. Hello, everyone. Can you hear me? Should we get started? Okay, great. Hello, everyone. My name is Minji Chen. I'm an assistant professor of electrical and computer engineering at Andlinger Center for Energy and Environment at Princeton University. Thank you, everyone, for being here for today's highlight seminar series. And it has been 2 years since we have in-person events. And this brings me to the old feeling of why do we have this community? And thank you for your support in being here. So today it's my pleasure to introduce Professor Philip Krein from University of Illinois, Urbana-Champaign, to talk about transportation electrification. Professor Krein is a legend in power electronics and has made tremendous contribution in many fields of power electronics, including the grid interface of renewable energy and transportation electrification. He is a past president of IEEE Power Electronics Society and is a member of the National Academy of Engineering. He's an entrepreneur and has a successful startup in the solar inverter industry. His publication and research has inspired many generations of power electronics researchers, including me and my student. So just for your information, this event is hybrid and we're broadcasting. So if you're in person, if you have any question, please raise your hands. We'll give you a microphone. And if you are remote, please type in your questions in the Q&A box in the Zoom. So without too much delay, let's welcome Professor Philip Krein.
Thank you so much, Minjie. And it's wonderful to help honor Princeton by being an in-person presenter here. For those of you on webinar, at least it's live, right? So we do hope for some good question and answer sessions and other things. And I want to talk today about electric vehicles. I'm gonna focus on consumer type vehicles, on automobiles, right? Of course, that space is very broad, and I'll touch on that quickly. But I want to put it in the context of the kinds of vehicles that you and I are driving, will be driving, will be developing, the kinds of things that will come out in the next 20 to 30 years. And in the context of that, I want to think a little bit about how things will change. The theme here is how do we make it easy? Okay, it's so desperately tempting to make everything really hard. Okay, it's not that hard. We can find easy ways to do these things. And I think that's really important. And I struggle all the time, interact with a lot of people who really want to do it the hard way. And you know, try to back them down a little bit and get them to think about that. So here in the next 40, 45 minutes, we'll see if I can give you some thoughts on that. You know, can we charge the cars up? Do they bring the benefits that we hope for? And I know this is working because it was before, but now it's complaining. So what I'm going to do is what you usually do. I'm going to pull the plug, put it back in, and that didn't help. And in fact, the arrows are not helping either. Well, the question is, what can I do and not damage the very sophisticated sharing that they've managed to do for the video here? Okay, let's see. Okay, yep. We're going to let them rescue us. Yeah, we lost it. Oh, the mouse works. Okay, now that works. Okay, no, that doesn't work.
Yeah, this one.
It does work.
Mm-hmm.
Okay, so touching the mouse reset it somehow. Mm-hmm. Okay, great. Okay, so support for this, some of it has come from my center at the University of Illinois, the Grainger Center for Electric Machinery and Electromechanics, and some of it has come from our joint institute with Zhejiang University in China. And a few of the results are actually motivated by some survey information that we've done over the years at Illinois and other places as well. So to give you that context, I'm trying to be beyond just being anecdotal and use some real data. Why electric cars? Why do we have hybrid vehicles? Why do we have electric cars? First of all, I would claim there are lots more opportunities that they provide for operation, for control, for performance, for autonomy. It's not that electric cars need to be autonomous or autonomous cars need to be electric, but it helps, right? It makes it easier. We've seen a lot of claims and demonstrations about extreme performance, things that shouldn't happen. A car that can do 0 to 60 in 2.5 seconds probably does not belong in the New Jersey Turnpike. I know how people drive on that road. You know, energy flexibility is as important as the energy reduction, and we'll see more about that. And you actually do get significant cost reduction. You know, drivers, users experience this, and they see how that works. And we'll come back to some of these things as we go along. Interesting thing to me, and I didn't just put this in unintentionally. Ira's son is in the audience, and I'll be eating dinner with him this evening. The capability we have now is finally pushing the envelope of what we literally had more than 100 years ago. Okay, that Detroit electric car was a high performance car in 1915. Okay, that particular 1914 model is still driving around here someplace. It did not drive to this campus today. I don't think it has that much range. But you know, it was the luxury car of its day. And that company, by the way, was put together by Henry Ford and by Thomas Edison. So, you know, these folks had plenty of familiarity with electric vehicles at the same time or even before they were doing combustion vehicles. Well, what are the problems, right? Limited range, where can I charge it? I'm trying to get someplace. I don't know whether I can plug in. I'm worried about that. Gee, I'm spending lots of money for batteries. Will they last long enough? That we have really good data on now. It takes a long time to refuel. I'll try to give you that. And there's other stuff too. I mean, my plug-in hybrid has half as much trunk space as the regular hybrid sitting next to it. Whatever. The cars are heavy. Are they comfortable? Gee, it takes a lot of energy to run the air conditioner. You know, people don't like this stuff. Can we deal with that, right? But there's some really important fallacies, and I want to emphasize this. I don't want to just read them. But there are plenty of people who come at it from the premise that an electric vehicle should match one for one everything you can do with a fueled vehicle. That just doesn't make sense, okay? Because the issue is personal transportation and personal mobility. The issue is not, I like my gasoline-powered car, right? So we have to go back to the more basic questions, and I'll talk more about that later. I sat through a workshop many years ago saying, oh, electric cars will never take off. Nobody's going to buy a car just for commuting. These cars are good for commuting. They're not good for anything else. And I looked around my neighborhood and I realized that virtually everybody I know has a car that they use almost only for commuting. But beyond that, differentiation in the automobile markets has really exploded. You know, there's different purposes for every vehicle. You know, why do you buy a Ford F-150? Why do you buy this SUV versus that one? Big and small, and a little sports car versus a sedan. So differentiation in the market is very broad. Fast charging needs a lot more thought, and we'll come a lot to that. And many people would claim that range is everything. We'll look at some actual data. And the interesting thing is behind this are some new models of mobility, okay? So I took that picture in Beijing. Okay, a few years ago, it was a big trend in China. They were going to have this bike sharing system with automated bikes with GPS. You could just grab a bike off the street and plug in your app and take it anywhere you wanted to go. Very quickly, they realized that that meant that there were thousands of bikes piled on street corners and other places. This was a pile I found near the entrance to Tsinghua University. You know, it just got way out of hand. And curiously enough, almost all of those companies went out of business. There's 2 or 3 of them left, but their business model just didn't make sense. You know, we're going to make all kinds of money. Doing what? I don't know, letting people ride bikes for free? That doesn't sound like a good way to make money, right? So business model issues are a real significant aspect of all of this as they develop. Now, there's some unexpected things. Electric cars are extremely fast and quick. Performance is excellent. This opens a lot of opportunities for active collision avoidance, for active safety systems, for a lot of things that we just don't think much about today. And electric transportation, as I'll try to walk through somewhat superficially, is actually a potentially very beneficial partner in the electricity grid. But we need the data. We need the user data. We need the driving data. And it's kind of trickling in at this point. We certainly don't have anywhere near what we need. Some people ask about scale. Well, it's hard to imagine scales bigger than electric locomotives doing freight duty and so forth. So there's plenty of very large electric vehicles already out there functioning. We know how to do this. Now, the fast dynamics are really an order of magnitude different than one is used to. I can change the torque in an electric machine 100 times per second without spending any extra money on the controls. If I want to do better than that, I could probably figure out how. But the easy one gives me 10 millisecond kind of response. So I can run that motor through its paces much more quickly than any human being can react, and far more quickly than I can do with a combustion device. What can I do with that, right? There's a lot of thought to do to make use of that. And by the way, that motor is absolutely off-the-shelf commercial catalog induction motor. That is not a special high-performance EV motor, although when you put it in an EV, it becomes a special high-performance EV motor that I bought out of a catalog, right? So the motor problem is not fundamentally the challenge, but the performance capability is really much different than we're used to in the past. Here's one example in active suspension. I'm not going to show you a picture of this, but there was a famous story many years ago. It was quite a long time ago, actually. One of the automotive OEMs had a significant project in active suspension. And they had a system that could perform so well that a driver could hit a curb at 60 miles an hour, and the car knew how to jump the wheels up, and the driver wouldn't notice it. Okay, and then somebody figured out, oh, this is a safety issue. Okay, this driver will run over pedestrians and not notice. Okay, so they had to back off. They had to start thinking more holistically. How do we put this together into a useful system? We can't just hit it with all the performance we can think of. But that performance does emerge in some other areas. So lately, we've been looking at this for fast actuation of aircraft controller surfaces and so forth. And then you look at this and say, wow, this is the same technology, and the performance you can get with it is again, orders of magnitude different than what you can do with conventional hydraulics and other things. This was always one of my favorites, active gear assist. Basically, we had a car where there was a manual shift lever that you could move around. And in the time that it took you to move from one gear to the next, the device would sense what you were doing, turn the torque off, disengage, adjust the motor for the new speed, re-engage, put the torque back on as you went into the next gear. The whole process took 150 milliseconds, and you can't move your hand that fast. Okay, nobody could. So, here you had a really interesting way to automate a manual transmission. There's no clutch or anything. The driver doesn't have to think much about this. And you actually get significantly better performance in the vehicle because you have the efficiency of a manual gear train with the capability of what we're more used to with automatic ones. John Deere took this to another level. So this is a hybrid electric loader. And basically, they've done this because it allows them to dynamically reconfigure all the energy on the fly. So that when the thing is stationary and digging into a pile, the energy can go to the shovel. And then when it's moving around, it can go to the wheels. And they can move it around to get the best efficiency moment by moment. And they're talking about 30 and 40% cost savings to the end user over life in the actual construction application. So their customers don't say, wow, it's hybrid, it's great, it's green. It's green anyway, because it's Deere. They say, it saves me lots of money and I can run it 24 hours a day. It's a good thing for all the things they do. And now they're talking about making these much more electric even. Electric and hybrid aircraft. If I were here 5 years ago talking about electric aircraft, it would be only entertaining, okay? Nobody took that seriously. Today, there are a lot of startup companies working on getting all electric aircraft certified with the FAA, okay? We're gonna see actual live aircraft flying around, not just package delivery drones, okay, in the skies, just a few years from now. They are in the certification process because it saves lots of fuel and energy and works really well in certain kinds of duty cases. This will not be the plane that I take from Newark to Hong Kong, okay? But it might be the plane that I take from Newark to Washington, for example, which is a much busier route. Okay, you start to get the idea. NASA's taken this a step further. This is strictly a concept platform. This one basically has a number of electric motors there in the back, electro turbines, and uses the fuel to drive a generator. So it's hybrid electric. The propulsion is all electric. And having that distributed propulsion actually gives them many more options that today we just don't have. Well, of course, when I have multiple motors, I can take this even a step further, whether it's independent wheel control or four-wheel dynamic control or active interactive wheel-by-wheel braking, all kinds of other things that a driver can't handle. So when we talk about automated driving, one of the questions is, how far do I go beyond what a normal human driver is capable of in terms of operating this? And maybe we can even get to the point, I mentioned automatic collision avoidance. Maybe we can do things like dynamic crush zone reconfiguration. When I really know I'm going to hit something, I have some time potentially to do something about it beforehand. In a hybrid car, there's many different things that we do. One example would be to try to use some kind of dynamic strategy to optimize the fuel economy. One of the intriguing things in the first generations of hybrid cars, and I'm thinking of the Honda Insight, the Toyota Prius, some of those very first ones on the market, is that every OEM could kind of take a totally different direction in terms of what they wanted to optimize. So for example, the early Honda cars were strictly about fuel economy. And their performance was a little bit rough around the edges, but they could go about 3 times as far on a given amount of fuel as a conventional, as the similar Honda fueled vehicle sitting next to it. Okay, the Toyota Prius was optimized more about emissions, and its emissions were dramatically, they were an order of magnitude lower than a similar size Toyota sedan. You know, what the public paid attention to is maybe irrelevant because of course that technology now is quite mature and lots of people are buying these vehicles. But, you know, what direction do you take it in? And it can go a little bit too far. You know, there have been some designs where they said, okay, we're going to optimize to get the best numbers on the federal or on the US federal urban drive schedule test. Okay, which may or may not have anything to do with real urban driving. And that's lovely, but it's, you know, maybe not meeting a real market need. And, you know, it's one of those things people should be trying to avoid, right? You don't want to design for the test, so to speak, right? Just like at the university, right? You don't want to just do the problems that are going to help you do good on the test. You want the ones that are going to help you learn the material, right? Of course, in the end, as I already mentioned, what matters is personal mobility, okay? And the question underlying this is how do we improve that? How do we revolutionize it? How do we make it safe? How do we enable it for everyone? And how does electric transportation and vehicle intelligence that maybe goes hand in hand with that, how does it help answer those fundamental needs? But you see how important it is to get away from, you know, existing thinking and say, because, you know, my gasoline powered car is not optimum, right? Not only do I hate going to the gas station, we'll talk more about that. You know, there's lots of other issues with it, right? And of course, you know, there's 100 fires in gasoline powered cars that we never hear about for every one fire we hear about in an electric car. And that doesn't mean that much, but it just means we've got to think differently. And this is going to have huge effect on the industry, right? One of the biggest companies from not so very long ago, a generation or two ago, Pullman Car Company, if you dig enough through the web, you'll kind of find out where they sort of still sit. They don't really exist though, okay? They've been washed out a long time ago. And, you know, Ford, GM, Chrysler, Fiat, where will those folks be in 20 or 30 years from now? Fortunately, they're turning around and trying to take some leadership in electrification and other things. Otherwise, they would become dinosaurs real quickly. Here are some challenging questions, right? How can I use a vehicle to get a kindergartner to a doctor? That's my test for autonomous transportation, okay? That's what I want to be able to do. How do I get rid of all the pollution from auto rickshaws in Bangkok and Mumbai and other places, right? How do I get my transportation system and my vehicles to relieve traffic congestion? You know, one of the real serious risks with autonomous cars is, you know, if I have my car drive me to work and then go find a parking space or go home, okay, do I have half of the cars on the road with no drivers at all, right? That doesn't sound like a way to reduce congestion. So it'll be interesting to see how that happens. Now, charging infrastructure is certainly a barrier in many different ways. It's a mix of reality and perception, and I want to hit a little bit of that. There are charge rate issues, and there is this underlying question of how do we, you know, should we emulate fueled vehicles? Here is a fast charger. Alicia took this picture at a conference, okay? Somebody spent a lot of time trying to make that look as much like a gas pump as they possibly could, okay? That's embarrassing, okay? If I spent my time trying to make my laptop charger look like a gas pump because I thought that was the way to do things, you know, I'd get laughed out of the room. So I don't know, I don't know. It's crazy, right? It turns out though, okay, I don't really need those outlets. I'm looking around the room for, wow, this room is really, this room doesn't meet code. You know, regular electric outlets, you all know what they look like. You all know, no, I'll forget wireless charging. Regular outlets can meet most of the need, and we'll see why that is as we go along, okay? We have early data that is telling us that owners of electric vehicles and plug-in hybrids don't use their cars the same way that people use gasoline vehicles. They seem to be looking for simplicity and convenience, not for ultra-fast charging and other things. Now, you know, there's caveats to that, and I'll come back to it. Average US daily car use, 29 miles. My colleague rightfully pointed out to me that that number is not very useful because, you know, what does that mean for the car I want to buy? Do I do the average? Do I do half the average? Do I do half the average early part of the week and double the average last? You know, what does that mean, right? So a more useful statistic is that less than 5% of trips in the United States are more than 31 miles. Okay, so 95% of trips in the United States are less than 31 miles. 95% of driving can be done with a car with a range of 31 miles. Now, that still may not be all that happy to a consumer, right? My gasoline power card tells me how desperately empty it is when the remaining range is 30 miles, okay, and how much I need to go find a gas station. But, you know, for an electric car, there's real data. Curious to me, maybe it makes sense to you, what you find is that the vehicle miles traveled per day tends to be the lowest in the highly populated areas. So it's actually lower in Los Angeles than what it might expect. And it's high in places like West Texas and other places that are dominated by rural areas where, you know, people do have to go 60 miles to the grocery store and so forth, right? So there is definitely a societal skew that is sort of an urban-rural divide that comes into play with transportation electrification. And that's a very real issue, and I don't have any wonderful answers about that. So the usual view when I ask people, and I try to get some recent data, they say, well, there's really only a very few electric vehicle charging ports in the United States. There's actually a map on the DOE website, you know, showing where they all are, and you can dig it all out. And they say, well, there's less than 80,000. What? Okay, there are hundreds of millions of electrical outlets in the United States, outdoors, ready to be used. Okay, so my objective, my intent is sort of to figure out how to turn each one of them into a potential charging point. And where we don't have them, you know, let's put them in, right? If I use conventional outlets, that's not going to work for long distance driving. Okay, I'm not going to get a 200-mile charge in any convenient way out of a conventional outlet, really. But I want to think of that as a separate issue. Remember, that was the 5% issue, right? So, you know, I want to use the 80-20 rule. How do I do the first 80% and make it easy? Really, to do this, though, it's not just a question of plugging in a car. You do need some level of vehicle to interface kind of interface, some communications. You want, the car has very sophisticated measurement equipment to monitor the state of batteries and so forth. As long as we can figure out how to secure that, there's no particular reason why that can't become revenue grade back to the utility. Okay, got to be tamper proof, but that can be done. And then the vehicle can actually communicate billing interface information, grid interfacing information that maybe we'll have a chance to come back to a bit. The vehicle charging is on board. That's another conversation, but it can do active safety management and all kinds of other things. The communication needs really aren't very high. If you think about that, you know, you're talking about so many bytes per minute or even per hour. You know, I may want to know what's the price of electricity right now. I may want to say, here's where my car is, and yes, it's connected. But this doesn't have to be a dynamic, interactive, real-time data stream using all kinds of bandwidth. Now, safety is often initial perception. I was forced to sit through a presentation by a leader of the Society of Automotive Engineers. I probably shouldn't even say this. He had all kinds of slides. He was talking about basically how unsafe electricity was. Okay, he was a mechanical engineer. Obviously, he's never lived in Calgary. Okay, you know, in Calgary, people have block heaters. They got to keep their cars warm in the winter. It's perfectly normal to go outside and in the snow and plug your car in. Nobody worries about dying because of the electricity. Okay, every one of those outlets is basically drawing about as much energy as an EV, as a small, you know, level 1 EV charger would be drawing. Okay, so I look at that and I see a forest of outdoor chargers, right? Nice and cheap, you know, and it's one of those things. Those things are, it's either the energy is so cheap that nobody bothers. You know, here's the outlets in our parking lot. Please keep your car warm so you can leave when you're done shopping. Or maybe, not in this kind of weather, but maybe there's a little coin operated thing next to it. You know, you put a quarter in and turn the knob. Don't make it hard, right? We do have hard problems though. I don't want to gloss over that. Software safety, hardware fail-safe safety, learning, testing and verification, testing software bugs, extremely non-trivial. How can I test these things enough to understand all their failure modes, to protect against their failure modes, to mitigate them? You know, these are the problems that are linked to autonomous driving. They're also linked to vehicle electrification. They're linked to fuel-powered cars as well. I mean, those problems don't go away, but certainly they come home to roost when the car is entirely operated by a software system. The power electronics in the car, primarily the charger, the drive interfaces, anything that's handling significant energy, certainly has plenty of potential capability for safety and interaction. So handshaking, ground faults, current limits, all kinds of lockouts and so forth. And I will show at least one sort of partial of a circuit during this, right? No equations, one circuit. It's not that hard to put together basically in a plug something that meets the legal requirements of what's called electric vehicle supply equipment. Everybody seems to think you need this big thing installed on the wall. No. Between the electronics in the car and something you can put in the plug, you got plenty of space. It's not that hard. Okay, and I can turn this on once it decides that the connection is valid, and so on and so on. It can adapt, you know, plenty of things one can do. Now, let's put this a little bit into context, okay? So-called level 1 charging. Basic outlet, 120 volts, essentially 12 amps. In my garage, I have a tool outlet like that one there on the lower left, the one to the right of the conventional one, which can do 220 volts, actually at 16 amps. 220 at 12 amps is also pretty universal. You know, these are things you can find everywhere in the world. And indeed, in the United States, code says that any residence has to have at least one outdoors as well. Now, you know, some people in rentals and other shared apartments and so forth don't have that kind of access, and we need to do something about that. But, right, these are your conventional outlets. All right, a well-designed electric vehicle can go about 4 miles on a kilowatt hour. So 250 watt hours per mile, roughly. If you take that basic outlet and you do something efficient, you find out that it's charging at about 5 miles per hour. This is a trick we took from Tesla a long time ago. They like to think of charging as equivalent to vehicle speed, right? So 5 miles an hour is pretty slow. On the other hand, my car is parked, what, 22 hours a day? Okay, so, you know, it's not driving 20 hours a day. And do a little bit of math and you figure out that, yeah, 60 kilometers each way, as long as you can get to this at work too, right, is quite plausible. Remember that 31 miles before? Okay, it's not that hard. And of course, if I have that tool outlet, I can do about double that, which, you know, makes life a little bit more convenient. You know, that's great, right? So if I drive 5 miles to a restaurant for lunch and they have an outlet and I can plug in, maybe by the time I'm done, I've recovered all the charge I just used, okay? Higher levels, okay? Level 2 charging is the most popular, and we'll see some pictures on the next one. That is not a level 2 charger. Very popular, lot of discussion. We start to see these as infrastructure on this campus. I saw several of them in the parking garage this morning. Very tempting to say, wow, this is great, right? Because it's much faster, 25 miles per hour. Now, that's still not going to get me from here to Pittsburgh, okay? So it doesn't meet the long distance drive thing. It takes my anxiety away because it gets me back to my 29 miles in, you know, an hour and a quarter or so. So this is the reason people do this, is because now I can put in my mind that, yes, I can go out to lunch, I can plug my car in. When I'm done, it's ready to go, okay? But if I'm parked all day at work, you know, I don't really need that. So I worry about whether this really has its place in the long run. Fast charging, of course, supports distance, and it's absolutely required. It's absolutely needed. Yes, we need them. I treat it as a completely separate issue. Certainly, most people who have vehicles use them as infrequently as possible because the energy is expensive inherently, and it puts a lot more stress on the batteries, a lot more wear and tear in the car. So you do that if you need to. If you're going from here to Pittsburgh, you want the fast charger access along the way somehow. But it's not the everyday thing. So the challenge, right, is you come up with this. This is a lovely little level 2 device that I found in China. And there is a level 2 device that I found in Bloomington, Illinois. Very similar, both, again, trying to look like gas pumps. All right. Okay, they're great. They're quite expensive to install. Yeah, they can support a longer distance commute. Certainly, they're going to make sense for some of the rural areas that we saw before, but it's not the same way, right? And they have even less relevance if one has a plug-in hybrid, and we'll look at that. Now, our campus experience is that these things are used on the average 8 hours a month, okay? Every place where we have level 1, just conventional outlets, you can't use them because there's already somebody plugged in. They're used all the time, okay? Now, it's not just the amount of money, which is ridiculous for these, but it's also that, you know, it's just so much easier, right? And I'm going to be plugged in all day. What the heck? All right. So you remember that data, right? 95% of US car trips less than 31 miles. So actual usage is mostly covered by basic outlets. Now, there's a challenge with that. We'll come to it in a few moments in terms of what it does to business models. But the nice thing is if I encourage an owner to be plugged in, okay, now I have a grid resource, right? My utility company can say, well, gee, you're going to be plugged in. Your car told me that today's pattern, like a Nest thermostat, right, is you're going to be plugged in until about 5:15 p.m. And you've told me that you want 4 kilowatt hours. Okay, well, I need to get you 4 kilowatt hours between here and there, but let me figure out how to do it as the utility provider, right? So I got time, I got flexibility, okay? And as the driver, I'm happy to sell that to PJM. You know, you give me some money for that, I will sell you flexibility. You still got to deliver me the energy, but you can figure out how. That's worth something. In the grid, that is worth something. We can, in fact, we can actually define the amounts these days. I can do a defined time. I can say, you know what? I don't have time for this. I'm taking a guest to lunch. My car's got to be full by 11:40 in the morning. Okay. And, you know, I'm plugged in now and I only got so many hours to get my 4 kilowatts. So just give it to me. And they say, okay, that's fine, but you're going to be paying 20% more for energy during this session, okay? True opportunity charging, meaning I just want to charge up and let me plug in wherever I can at grandma's house or whatever. And sort of this non-routine locations. This I think is interesting. you know, if I'm at my grandma's house, can my car tell that utility, bill me for this energy, don't bill my grandma? Okay, we know how to do that with cell phones. We do that constantly. Okay, we don't know how to do that in the electricity grid. It's kind of a mess. If I'm at the shopping mall, all right, do they want to give away 20 cents worth of energy in exchange for me coming in and buying some stuff? Guess what? Okay, certainly the restaurant, right? If they can get a few more customers by giving away 20 cents worth of energy an hour, you know, that's a win, right? And the price at night is much lower, right? So everybody likes to use our average 12 cents per kilowatt hour, and I know in Jersey it's quite a bit higher. But no, that's not what it costs to charge an electric car. My car is programmed to charge between 2 a.m. and 5 a.m. Power is not 12 cents a kilowatt hour at 3 o'clock in the morning. It's not. There are times of the year, actually, when the price is negative at that time of day. That's because we have a local nuclear plant and nobody wants to turn it down. And when the load goes low enough, you know, they'd rather give away the energy from that plant than have to turn down the knobs, okay? I like charging at that time of year. It's great. It's a lot of fun, okay? Now, people say it takes a long time to charge an electric car. Oh, I've had lovely discussions about this, okay? Yeah, it takes hours and hours to charge your car. No. When I go home, I pull in my garage. Yes, I have an outlet in my garage. It takes me 8 seconds to go over, get the connector, open the flap, plug in the car. 8 seconds. Next morning, I come out, takes me 8 seconds to disconnect, close the flap, put up the cord. Takes me 16 seconds to charge my car. I don't care how long it takes the utility. Makes no difference to me. I'm in my house doing something else, okay? Same thing when I'm at work, right? When I go to the gas station, because I have a plug-in hybrid, I got to get in my car, drive over to the gas station, get out, do this stupid credit card thing that takes me a lot more than 8 seconds, okay? Get the pump in this smelly, noxious stuff that I really don't want on my hands, right? You know, the whole process, going to the station, doing the work, paying the, you know, takes probably 20 minutes, all right? So I can charge my car, you know, 60 times in the amount of time it takes me to go to the gas station. So I'm not going to the gas station unless I have to for long distance driving, right? So as soon as you have a plug-in hybrid, you learn real quickly, I hate gas stations, okay? And I certainly equally am going to hate fast charge points for the same reasons. You know, I'll use them when I have to. That's okay. The Census Bureau estimates about 111,000 gas stations in the United States as of about 5 years ago. And of course, almost all fuel is distributed from those locations, right? Nearly 100%. But you can see that, I'm getting ahead of myself a little bit here. You can see what's happening, right? We're looking and realizing that probably at least 95% of electric vehicle driving can be done from home and work, right? And the energy is different because it's long distance. In the end, you figure out that maybe 10% of the energy will come through this fast filling station model. Now that's a huge change, right? These folks have 100% of the energy market for transportation. The fast charging folks are going to have 10%, okay? The business model is not going to map over. And whether they're going to have enough money to do the investments to come up with 110,000 serious stations where people can charge is a big question. And we'll see what happens with that. I'm very concerned about that, actually. Now, energy, a little bit about the benefits, right? So fuel vehicles convert on the order of 20% of their fuel energy to wheel power, and you stack up the refinery and everything else. You get an overall percentage of maybe 15, 18%. well to wheels, so to speak. It's actually, that's a little optimistic, but you get the idea. Electric vehicles are much better at converting, certainly not perfect. Here in New Jersey, a lot of them will be getting their energy from combined cycle plants, which are thermally fairly efficient, 40%-ish well to wheels. And there are other sources. When you actually walk through the data that's starting to come in, again, you see that electric transportation uses about 1/3 as much primary energy per unit distance as combustion vehicles, going all the way back to the source. That's a factor of 3. That's pretty substantial. That makes a big difference in fuel use and emissions and everything else. And of course, if you're in the right place, you can kind of direct your energy. So when I'm charging late at night, I'm using nuclear energy for my car. And if I'm charging in the middle of the day in the right places, I'm using solar energy for my car. That's why the parking lots in Silicon Valley are all covered with solar panels and so on, right? At the right times of day, I could be using wind. Hard to do that with a fuel-driven car, right? Flexibility is again, something I can sell to the grid. If my car's connected, then my charger becomes a potential resource for voltage regulation, for frequency regulation, for some dynamic things on the grid, especially if it's not quite full yet. I don't necessarily have to pull energy back out of it. This is one thing we've been working on for a long time. Does the energy flow need to go both ways? The answer in general is no. I might want it if the power goes out. That's a different issue. Do I want the utility to discharge my battery? No. Am I willing to let them charge it at 3 o'clock in the afternoon instead of 11:30 in the morning? Sure. Okay, I can monetize that too. And you can start to see how I can optimize things. I could try to get lowest cost, lowest stress, do something as gradual as I can and so forth. And maybe I can incentivize things to make that work out for folks. The vehicle can manage its own thing and decide whether I should bill the owner or whether I should bill the owner of the outlet. So my shopping mall can put themselves in a database and say, here's a bunch of outlets, charging from these outlets is free to whoever's plugged in, bill the mall owner, right? Or at grandma's house, I can send the message saying bill the car owner. And one can imagine a mix of those at different places. It's not that hard to imagine many kinds of metering strategies. And indeed, it's interesting to imagine parking lots where an aggregator kind of puts these together and manages it a little bit as a fleet, then sells services back to the grid, okay? Provisioning the infrastructure, the outlets we talked about, right? Basic outlets are not going to be smart. They're going to be dumb outlets. And they might be in a database or maybe not. But the car is smart. The car knows where it is. The car can say where it's parked. The utility can come back and say, yes, this outlet's in the database, or no, it's not. Again, it's not that hard. And I'd like to have pricing signals to kind of make this work as well. So a little bit wrapping up here, less than 10% of charging energy is likely to come from fast chargers. Vastly different business model than conventional fuel. Fast charging will also be a lot more expensive, and you can focus on particular areas. People ask about battery swaps, and I'm going to save that in case somebody wants to ask the question. There's all kinds of interesting things we can say about it, but they're a little bit beyond the scope here. So yeah, electric vehicles have significant benefits. Very much reduced energy usage, high performance, a lot of benefits for mobility in general. And in fact, 95% of those commuting requirements and driving requirements can be resolved if you only have access to a conventional outlet. Now, I don't want to minimize that. There's plenty of people who don't. Okay, it's very hard when you are living in a dense apartment complex to find a place to plug something in. Okay, we can fix that if we put in regular outlets. It's not as big a deal. It's certainly trivial in new construction. It's possible even at streets. We saw the outdoor parking lot in Calgary, plenty of outlets, not that hard. And the vehicle can manage safety and billing and a lot of other things. And with that, I would like to pause and make sure we have at least a bit of time for questions. So thank you very much.
Thank you, Bill, for this wonderful 1 hour journey. So any questions from the audience here?
And I know we have some folks who'll be looking at the chat as well.
All right. I don't know if you have the answer to this, but I've been seeing a lot of these electric airplane prototypes coming out, and they look a lot different than a normal airplane. Usually will have like 10, sometimes 24 turbines on it. I'm curious if you know what design decisions are going into that versus more conventional aircraft like 4 turbines on it.
Yeah, so the in case anybody didn't catch the whole question, it was really some of the propulsion issues with respect to electric aircraft. Turbine-based aircraft, the turbine system works better if it's scaled up. So turbines are more efficient, they're more functional, they work better when they're made bigger, right? So that's why we ultimately even see long-range jetliners that have only 2 engines. They can't quite get away with 1 engine that doesn't survive the safety requirements, but they can get down to 2. With electric propulsion, I don't have the same scaling issues. So I can do things at many different scales. And there are a lot of things that one can do with distributed propulsion. And indeed, for example, you can do differential propulsion during cruising, during takeoff, during landing. Much different flexibility that you really can't do with a turbine system. People are there's some good knowledge about that, and they're learning more, I think, pretty quickly. But distributed propulsion in an aeronautic context offers a much different set of trade-offs and significant benefits in terms of how you manage the energy flows. That's why they look so much different, yeah.
I think you might have chosen somebody else, but so you mentioned it earlier just briefly, using the battery of the electric car to power your house. You know, I came from the Bay Area, now I'm in New Jersey, and I'm seeing that there's a lot of power losses here. I've got 2 65 kilowatt hour batteries in my driveway. What are the prospects for this?
Well, the fundamental issue with trying to use a battery both ways, right, is of course you're going to wear it out more quickly. There's clearly a big difference between saying, okay, my power typically might go out a few minutes a year, and it's great to have a backup. And sure, the battery pack in my car is a helpful potential thing for that. I may want to limit the power flows and not grab whatever I could normally get from my house, but that's a nice feature, right? The issue is less that, there are many people who talk about sort of active bidirectional support for the grid. And that adds 2 additional problems, which is number 1, everything in the grid all the way to your car has to be functional and safe both ways. And that's non-trivial and actually fairly expensive. And the second is I lose control over how my battery pack is being employed and the wear and tear and so forth. And I got to figure out, how much should I be renting that to the utility with? So I think we can separate that out. Using your car for backup, it's not trivial, but makes sense and is something, of course, that a lot of us would love to be able to do. But using it in a direct bidirectional way with the utility is an expensive proposition that I really think doesn't have enough benefits to justify that. In some countries, they're looking at that more seriously, but I don't think that makes a lot of sense here. Yeah, I think there was one there on the aisle, right?
Hi there, thank you. I wanted to ask, you said that you can basically do charging from a normal outlet. So why hasn't that been done widely? Is there a detriment to battery health? And then additionally, when you're managing fleets, is it is it possible that utility might be able to manage battery health on a fleet scale?
Well, let me answer that question in two ways. So your question was both about battery health and kind of conventional outlets. We have learned so much in the last 20, 25 years about managing battery health that has been a huge game changer. I was telling somebody last night that I remember going to an OEM many years ago, early when we were working on EVs, and we had a really interesting technology for battery health management. And we presented it to this OEM, you know, and walked through, here's data, here's how it functions, here's why it's a great thing. And at the end, they stopped us and they said, you know what? It isn't, yours won't work. Won't work? What are you talking about? What's the issue? They said, well, we tried this one. It didn't work. We tried this one. It didn't work. We tried this one. It didn't work. So yours isn't going to work either. Okay, so fortunately, eventually we got past that. Today, battery management is absolutely a critical feature in the software of all of these vehicles. And monitoring the batteries, balancing them, checking for thermal mismatches and everything. That's why batteries in Teslas are lasting 200,000 miles, because we know how to manage them. When Toyota first came out with the Prius, it was very uncertain whether those batteries were going to last. Now, the nice thing about a conventional outlet is it basically forces me to charge batteries slowly. Batteries are always happier when they're being charged slowly. Lithium-ion batteries, by the way, are also happy when they're not full. Okay, the easiest way for you to destroy your laptop battery is to keep it plugged in all the time and full all the time. You know, a recent laptop actually has a management thing in it that will turn the charger on and off and force the batteries to cycle some. But that's how you kill lithium-ion batteries. You just keep them full 100% time and on charge. So yeah, we've learned a lot about battery management, and conventional outlets actually you know, encourage good behavior in some sense.
Thanks everyone. Let's switch our focus to online audiences. So if you have any questions, let's stay here and interact after the seminar.
Sure.
So there's a very interesting question online. So one of the main takeaway of this seminar is that EVs doesn't have to be one-to-one replacement of conventional vehicle. But the question is, if in 20 years or 30 years, it's all EV, and then it has to satisfy all people's needs. And what would be your comments on this?
Right. So the question is great, right? So EVs don't have to map one-to-one to conventional vehicles. But absolutely, when EVs are 100%, they have to meet all conventional needs, okay? But do you hear how those two are very different, right? Meeting conventional needs isn't the same as using the vehicles we have today, okay? My fuel-driven car that sits next to my plug-in hybrid only gets fueled up once every month or 6 weeks, okay? It doesn't get fueled up every day. You know, could I fuel it every week? Well, yeah, there's plenty of people who fuel their cars every week. So, you know, what's the best model? What's the best mapping to mobility? And the real reason I can't go much farther in answering that is because all of us know, right, that autonomous cars, Uber and Lyft and other players are coming in, and the nature of transportation is likely to change as quickly as anything else. And then, you know, part of the question will be, okay, how do electric vehicles map into this? And to take that just one step further, you know, one of the questions is what do I do if I want a car to be driving 22 hours per day instead of 2 hours per day? And how does that change the picture? You know, and that's when you start talking about battery swaps and some of these other kinds of things that you know, don't make sense in the other context. So, you know, how is this going to play out in the development of new kinds of transportation modes and models? And you know, very uncertain, but, you know, it doesn't have to match what we do today with fueled cars.
Thank you. There's another very good question. Can you comment a little bit on the new pressure or stress on the electric grid and how do you deal with the second life benefit?
Mm-hmm. Well, it's an interesting question about, you know, how does this affect the grid? Very frustrating to me. A few years ago, we had lots of utility providers who were basically trying to discourage electric cars. Okay, I don't remember too many industries that like to discourage new customers. Okay, so you know that's going to change, but you know, put a scale on it. Okay, today in the United States, about 26% of primary energy goes to transportation, and about 40% of primary energy goes to electricity generation. Okay, if 30 years from now we have all electric transportation, that means our grid has to grow by something like 60, 70%. Okay, that's a massive change. So yes, we can integrate a fair amount of this into the existing grid, but we don't have the capacity to take it all the way through, you know? So it's new generation, new plants, and everything else. Now, I hope that's a good problem to have. The industry loved this problem in the 1950s, right? When we built lots of power plants to handle everybody buying new appliances and having electricity use throughout their homes. I certainly hope we get to that same attribute in transportation. The good news, right, is that transportation makes a better match to renewables, which, you know, are more intermittent, less timely, but I have flexibility in my electric transportation loads. If I can match that flexibility against my resources, I can get a lot of benefits. So yes, massive change is coming. And I don't know whether everybody's looking forward and ready for it.
Great, I think that's all we have for today. If you have any questions, feel free to stay. We're running out of time on our audiences, so we'll let that come out and you can stay and interact and ask questions. So just one announcement, our next highlight seminars will be next Thursday from Professor Endowed of Sustainable Architecture Design and Professor School of Environment at Yale University. The talk will be about toward ecosystem of systems research development in architectural sciences. So I would thank everyone for being here. This is a big step for us to going back to normal. I would thank Professor Krein for being here and going to talk in person. That is very important. You can feel the difference between a hybrid or virtual seminar and an in-person seminar. And finally, I will thank our Andlinger Center supporting team, Sarah, Diana, Diane, Rob, Thumper, and Maureen. Let's give everyone a big clap.
Thank you, and thanks to our webinar audience. And I'm here for a few more minutes if there are a few more questions. Mm-hmm.